Swayam Prabha. Digital India. Educated India.
Hello learners, I am Dr. Rekha Sharma, retired professor UGC Human Resource Development Center, Rashtrasanta Tukaroji Maharaj, Nagpur University, Nagpur. In this video, we shall study rancidity in fats and oils. The objectives of this module are: after studying this module, the learners will be able to state what is rancidity. They will be able to differentiate hydrolytic and oxidative rancidity. The learner will be able to describe the mechanism of rancidity and will be able to discuss the factors responsible for rancidity. Now, stability of fat. The stability of fat or fatty food is significant to maintain a fresh taste or odor during storage and use. The stability is related to the composition of the fat moiety and the changes it is subjected to. Fats with substantial unsaturated fatty acids are usually unstable. The presence of agents causing oxidation, that is pro-oxidants, or preventing oxidation, that is antioxidants, and the methods of storage determine their stability. Vegetable fats are usually more stable than some of the animal fats such as lard, even though the degree of unsaturation of the vegetable oil may be greater. This is attributed to the presence of natural antioxidants in them. The food products undergo chemical changes in flavor due to the chemical changes occurring in fats and oils present in them. The causative factors responsible for such a change are atmospheric oxygen, the presence of enzymes, and the application of high temperatures. Now, rancidity. The change that a lipid undergoes leading to an undesirable flavor and odor development is known as rancidity. This is brought about in two ways: hydrolysis and oxidation, giving rise to hydrolytic rancidity and oxidative rancidity respectively. One occurs when oil reacts with oxygen and is called oxidative rancidity. The other cause of rancidity is a combination of enzymes and moisture. Now, hydrolytic rancidity. Free fatty acids cause problems in foods because they produce off flavor, reduce oxidative stability, cause foaming, and reduce smoke point. That is the point or the temperature at which an oil begins to smoke. If the liberation of free fatty acids from the glycerol backbone results in the development of off flavors, for example, volatile short-chain free fatty acids that form off aromas or long-chain fatty acids that form soapy tastes is known as hydrolytic rancidity. Free fatty acids can be liberated from triacylglycerols by enzymes called lipases. Hydrolytic rancidity occurs when the fat is broken up into free fatty acids and glycerol in the presence of water. Hydrolysis is catalyzed by acid, bases, enzymes, or thermal effects. When the base is the hydrolyzing agent, the liberated fatty acids are converted into their salts or soaps, and the hydrolysis is termed as saponification. The other agents release free fatty acids and the reactions brought about by them are collectively known as lipolysis or hydrolytic rancidity. The presence of the enzyme lipoprotein lipase quickens this process. Rancidity in foods may be very slight, indicated by a loss of freshness, to very severe, indicated by objectionable odors and flavors. Hydrolytic rancidity occurs chiefly in raw milk due to the hydrolysis of milk fat, resulting in the release of short-chain fatty acids. The flavor of rancid milk is due to even-numbered fatty acids from C14 to C12 and is not just due to butyric acid as people commonly believe. Free fatty acids are absent in the fat of living animal tissues but are formed by enzyme action after the animal is killed. The temperatures of rendering animal fats are capable of destroying the enzymes responsible for hydrolysis. In the oil of oilseeds, a substantial amount of free fatty acids are present at the time of harvesting only due to hydrolysis. So, the oilseeds require neutralization with alkalis after they are extracted. Lipolysis seriously degrades the quality of frying oils as large quantities of water are introduced into frying oils from the food along with the high frying temperatures. The smoke point of fat is seriously depressed due to lipolysis. For example, the smoke point of cottonseed oil decreases from 232.2 degrees centigrade to 160 degrees centigrade in the presence of 1% free fatty acids. Foods fried in such oils exhibit browning, cracked surfaces, and show increased fat absorption. After lipolysis, the free fatty acids form polymers, the viscosity of the fat increases, the color darkens, and the quality of the fat deteriorates. This is known as polymerization. Polymers decrease the heat transfer efficiency of oils and also affect the quality of products fried in it. Lipolysis can cause changes in fats and oils which can be minimized by their proper handling. On the contrary, in some foods, lipolysis is done deliberately to develop a typical flavor. For example, in different varieties of cheese, yogurt, and bread, controlled lipolysis is used. Now, oxidative rancidity. Oxidative rancidity is associated with the degradation of fat by oxygen. The double bonds of an unsaturated fatty acids can undergo cleavage through a free radical process, releasing volatile aldehydes and ketones. The fat oxidation process resulting in rancidity begins immediately after the animal is slaughtered and the muscle fat, intramuscular, intermuscular and surface fat become exposed to oxygen in the air. This chemical process continues during frozen storage, though more slowly the same thing happens with vegetable oils also. Now, mechanism of oxidative rancidity. Rancidity takes place through auto-oxidation because the rate of oxidation increases as the reaction proceeds. Oxidation takes place through a free radical chain mechanism involving three stages. First is initiation. Here, the formation of free radicals takes place. Second is propagation. This free radical chain reaction is there. Third, termination, that is formation of non-radical products. Now initiation. In initiation part, hydrogen is removed from the fatty acid chain to yield a free radical. The removal of hydrogen from the fatty acid chain takes place at the carbon atom next to the double bond and can be brought about by the action of light or metal, etc. For example, in oleic acid, the reaction will proceed with the removal of hydrogen from carbon 8 or 11, resulting in free radicals. Now propagation. Once a free radical is formed, it will combine with oxygen to form a peroxy-free radical, which can remove hydrogen from another unsaturated molecule to yield a peroxide and a new free radical. This is called propagation reaction. This reaction may repeat up to several thousand times and takes the shape of a chain reaction. Termination. If the free radicals react with themselves to yield non-active products, then the propagation reaction is changed to termination reaction. The hydroperoxides formed in the propagation part of the reaction are the primary oxidation products. They are generally unstable and decompose into secondary oxidation products, which include a variety of compounds. Among the secondary oxidation products, aldehydes and alcohols form an important group. The volatile aldehydes are mainly responsible for the oxidized or rancid flavor of fats. This is the generalized scheme for auto-oxidation of lipids. Now reversion. Many oils and fats undergo a change in flavor before the onset of rancidity, which is known as reversion. The name reversion came to be applied to the change because some marine oils which possesses a fishy flavor before processing revert to this fishy odor on storage. The term is poor because the flavors which developed in most fats were never before, but it has become firmly established and cannot be displaced. The flavors which develop are quite different from rancid flavors. Soybean oil, which reverts readily, is described as developing first a buttery or beany flavor, then grassy or hay-like, then painty, and finally fishy. The factors which are known to influence the onset and development of reversion are: first, temperature; second, light; third, oxygen to a limited extent; and fourth, trace metals. As the temperature of storage increased, the length of time in which reversion flavors can be detected decreases. It is light in the blue violet and from 325 to 460 nanometer, which causes reversion changes. Oxygen is not necessary in large quantities for the development of reversion, but a small amount appears indispensable since flavor changes which occur in oils stored in vacuum or under inert gases are not characteristics of reversion. Copper, cobalt, chromium and zinc cause an acceleration in reversion. Aluminium, tin and nickel are not so active. During the process of fats, compounds are often added which have the ability to form complexes with metal ions. These are called metal scavengers, since they remove the ions from the field of action and inhibit their catalytic effect. Rancidity and reversion are not the same thing. Some oils and fats are susceptible to rancidity, such as corn oil, are reversion resistant. The flavor changes which occur during reversion vary with different fats, but in rancidity, the final flavor is the same for all fats. Now, factors influencing lipid oxidation. Food lipids contain a variety of fatty acids that differ in chemical and physical properties and also in their susceptibility to oxidation. In addition, foods contain numerous non-lipid components that may also oxidize and interact with the oxidizing lipids and their oxidation products. Oxygen concentration, temperature, and moisture are the other factors influencing autooxidation. Now, fatty acid composition. Cis acid oxidize more than trans isomers, and conjugated double bonds are more reactive than the non-conjugated ones. Autooxidation of saturated fatty acids is extremely slow. At room temperature, they remain practically unchanged when oxidative rancidity of unsaturated fatty acids become detectable. At higher temperatures, however, saturated fatty acids can undergo oxidation at significant rates. Now, oxygen concentration. When oxygen is abundant, the rate of oxidation is independent of oxygen concentration, but at very low oxygen concentration, the rate is approximately proportional to oxygen concentration. However, the effect of oxygen concentration on oxidation rate is also influenced by other factors such as temperature, surface area, moisture, and pro-oxidants. Temperature. In general, the rate of oxidation increases as the temperature is increased. Temperature also influences the relation between rate and oxygen partial pressure. As the temperature increased, changes in oxygen partial pressure have a smaller influence on the oxidation rate because oxygen becomes less soluble in lipids and water. Now, surface area. The rate of oxidation increases in direct proportion to the surface area of the lipid exposed to air. In oil in water emulsions, the rate of oxidation is governed by the rate at which oxygen diffuses into the oil phase. Now, moisture. In various fat containing foods, the rate of oxidation depends strongly on water activity. In dried foods with very low moisture content, oxidation proceeds very rapidly. Increasing the moisture content to a little extent retards lipid oxidation, and this protective effect is believed to occur by reducing the catalyzing activity of metal catalysts. At somewhat higher water activities, the rate of oxidation increases again, presumably as a result of increased mobilization of catalysts and oxygen. Now, pro-oxidants. Lipid oxidation is often referred to as autooxidation. The prefix auto means self-acting. Thus, the term autooxidation has been used to describe the self-perpetuating generation of free radicals from unsaturated fatty acids in the presence of oxygen that occurs during lipid oxidation. Pro-oxidants, which are found in virtually all food systems, are compounds or factors that cause or accelerate lipid oxidation. Many pro-oxidants are not true catalysts since they are altered during the reaction. For example, singlet oxygen is converted to a hydroperoxide and ferrous ion is converted to ferric state. Transition metals, particularly those possessing two or more valency states and a suitable oxidation reduction potential between them, are effective pro-oxidants. Examples of such metals are cobalt, copper, iron, manganese, and nickel. In concentrations of even as low as 0.1 ppm, they can decrease the induction period and hence increase the rate of oxidation. Trace amount of metals is encountered in fats from soils where oil seeds are grown, from animals in the case of animal fats, and from metallic equipment used for processing or storage of fats and oils. Now, heat and light. Presence of heat and light accelerate the rate of reaction of fats with oxygen. That is, heat accelerates autooxidation. Heat and light act as the energy source for the production of free radicals in rancidity and reversion of oils and fats. Now, antioxidants. An antioxidant is a substance that is added to fat or fat containing foods as a preservative to retard the oxidative breakdown of fat. An antioxidant should be fat soluble, effective in low concentrations, and should not contribute any objectionable flavor or color to the fat or foods to which it is added. Antioxidants combine with free radicals, interrupting the free radical chain mechanism. There are 5 types of antioxidants. First, natural oxidants. Second, synthetic antioxidants. Third, semi-synthetic antioxidants like gallic acid, propyl gallate. Fourth, metal chelators like citric acid, phosphoric acid. And fifth, oxygen scavengers like ascorbic acid. Now, natural antioxidants include polyphenols or flavonoids, ascorbic acid, that is vitamin C, and tocopherols, that is vitamin E. The natural antioxidants tend to be short-lived, so synthetic antioxidants are used when a longer shelf life is preferred. Synthetic antioxidants include BHA, BHT, TBHQ, propyl gallate, and ethoxyquin. Again, antioxidants can be categorized as primary antioxidants and synergists. Primary antioxidants operate directly to inhibit autooxidation by donating a hydrogen to the free radicals, thus breaking the chain reaction. For maximum efficiency, primary antioxidants are often used in combination with other phenolic antioxidants or with various metal sequestering agents. Synergists are compounds that prolong or enhance the antioxidant action of primary antioxidants. Some commonly used present antioxidants in fats and oil, and their characteristics are tocopherols, butylated hydroxyanisole, that is BHA, and tertiary butyl hydroxyquinone, that is TBHQ. Now, tocopherol. These are the most widely distributed antioxidants in nature, and they constitute the principal antioxidants in vegetable oils. A relatively high proportion of the tocopherols are present in crude vegetable oils, which remain in sufficient quantities in finished oils to provide oxidative stability to the final products. Now, butylated hydroxyanisole or BHA. It has found wide commercial use in food industries. It is highly soluble in oil and shows weak antioxidant property, particularly in those oils which are rich in natural antioxidants. It is relatively effective when used in combination with other primary antioxidants. BHA has a typical phenolic odor that may become noticeable if the oil is subjected to high heat. Now, tertiary butyl hydroquinone, that is TBHQ. TBHQ is moderately soluble in oil and slightly soluble in water. In many cases, TBHQ is more effective than any other antioxidant in providing oxidative stability to crude and refined polyunsaturated oil without the problem of color or flavor stability. Addition of sequestering agents. Sequestering agents bind metals, thus preventing them from catalyzing autooxidation. Examples of sequestering agents include EDTA, that is ethylene diamine tetraacetic acid, and citric acid. Now, coming down to storage of fats and oils. Fat should be stored in a cool place, covered and away from strong odors. They should be packaged to prevent oxidation. Oils should be stored at ambient temperature in sealed conditions. Once a container is opened and fats come in contact with air, the shelf life is reduced. Therefore, opened containers should be used relatively quickly. Once rancidity develops in fats or oils, they cannot be made palatable. All fatty foods experience deterioration even when handled and stored under ideal conditions. Brown rice, wheat, or any whole grain flour contains germ and bran, which has a lot of fat and creates further challenges for long term storage. Low fat beans store longer than high fat ones. Nuts go great in cans, but nothing can stop the oils in them from developing rancidity over time. That's why every precaution has to be taken while storing whole grains and high oil content foods. In addition, rancidity can be controlled to some extent but not completely eliminated. The ways to slow down rancidity are the very same general rules used for all foods in long term storage, that is, keep it cool, keep it out of sunlight, keep it out of oxygen, and keep it away from water. Do not add fresh oil to vessels containing old oil or used oil. The old oil or used oil will trigger a reaction and the new oil will become rancid far more rapidly than if the oil was stored in a clean, empty vessel. Avoid using vessels that are wet. This will also speed up the problems associated with oxidation and allow tanks to drain and dry adequately before use. Packaging and shelf life. Solid fats and liquid oils are often sold in cans, plastic bottles, or pouches. Oils are rarely sold in glass containers anymore. Metal cans are the most resistant to long-term oxygen transfer, that is, transmission of oxygen through the material over time. Plastics are not that resistant to oxygen transfer and will allow significant oxygen levels into the container in 1 to 2 years. All fat or oil products experience deterioration even when handled and stored under ideal conditions. Oils that do not require heating to remain liquid resist deterioration more than the higher melting products. Most shortening and other similar products will maintain an unacceptable flavor and oxidative stability for 2 or 3 weeks in melted form with adequate controls. Now, measurement of oxidative stability. Oxidative stability is a measure of a fat's resistance to oxidation. Because the process takes place through a chain reaction, the oxidation reaction has a period when it is relatively slow before it suddenly speeds up. The time for this to happen is called the induction time. There are a number of ways to measure the progress of the oxidation reaction. One of the most popular methods currently in use is the Rancidity method. Now, this Rancidity method is carried out using an air current at temperatures between 50 to 220 degrees centigrade. The volatile oxidation products, largely formic acid, are carried by the air current into the measuring vessel, where they are absorbed in the measuring fluid or in the distilled water. By continuous measurement of the conductivity of this solution, oxidation curves can be generated. The cusp point of the oxidation curve, that is the point where a rapid rise in conductivity starts, gives the induction time of the rancidity reaction, which can be taken as an indication of the oxidative stability of the sample. Now, let us summarize. Lipid oxidation is one of the major causes of food spoilage. It is of great economic concern to the food industry because it leads to the development of various off flavors and off odors, generally called rancidity, in edible oils and fats containing foods, which render these foods less acceptable. Autooxidation is the chief reaction involved in the development of rancidity. This takes place through free radical mechanism consisting of 3 steps: initiation, propagation and termination. It is influenced by fatty acid composition, oxygen concentration, temperature, surface area, moisture and pro-oxidants. Hydrolytic rancidity occurs when the fat is broken up into free fatty acids and glycerol by the presence of water. This reaction is catalyzed by acid, bases, enzymes or thermal effects. Antioxidants are added to retard the oxidative breakdown of fat and thus prevent spoilage of foods. Literally hundreds of compounds, both natural and synthesized, have been reported to possess antioxidant properties. Fat should be stored in a cool place, covered and away from strong odors. These should be packaged to prevent oxidation. Once rancidity develops in fats or oils, these cannot be made palatable. The Rancidity method is a measure of the progress of the oxidation reaction. These are the references. With this, we have come to an end of the lecture on rancidity in fats and oils. Thank you.